Hi everyone, my name is Jian Zhu. I'm a PhD student at UMass Lowell, and here I'm presenting our collaborative work with our colleagues from Arizona State University on design and evaluation of an invariant extended Kalman filter for trunk motion estimation with sensor misalignment. For a wearable robot to function autonomously with different users in various tasks, it needs to collect sensor data to understand human states and intents in real time. And it is crucial to estimate the human states. For example, pulse and velocity estimation of the body is a special interest in gait analysis and wearable robot control design. Recently, extended Kalman filter has been applied to estimate body pulse and velocity and address the nonlinearity in the kinematic chain. Yet conventional InEKF suffers the major weakness that its design relies on the linearization of the process and the measurement models at the state estimates instead of the true states. Due to this weakness, the InEKF cannot guarantee error convergence under large initial estimation errors. Recently, Invariant Extended Kalman Filter has been introduced to ensure real-time, provable error convergence even in the presence of large initial estimation errors. In a recent work, it has been applied to a leggy robot estimation problem. While the InEKF method has achieved impressive estimation performance for robot locomotion, it has not been applied to solve some of the key challenges in the state estimation of continuous human movement states, such as inaccurate kinematic parameters and imperfect sensor placement. By imperfect sensor placements, here we mean the misalignment and the offset between where the kinematic measurements are drawn versus where the MU is placed. One common solution to imperfect sensor placement is manual sensor calibration, which is often time-consuming and thus may not be suitable for real-world applications. Motivated by this, we introduced an InEKF with explicit treatment of the sensor misalignment that produce real-time state estimates and rapid error convergence of the body pose and movements, even in the presence of significant sensor placement offsets and large initial state estimation errors. As the state variables of InEKF lie on the lead group, the representation of the error between the estimate and the true state trajectories will be different from the error representation of the conventional EKF. For InEKF, the system dynamics has to satisfy the group affine condition. Given that, we can show that the invariant error is state trajectory independent. Also, the measurement model of InEKF has to be the invariant form, so the innovation part can also be the state trajectory independent. Since the filter objective is to estimate the body movement, our state variables are MU orientation, velocity, and position in the wall frame, and the placement offsets in the MU frame as shown in the figure. The process model is based on the MU motion characteristics. We assume the placement offsets are constant over time, so we model their dynamics as 0 plus small zero mean white Gaussian noise. We could also show that the deterministic system dynamics satisfy the group affine condition. In this paper, we cannot directly use relative fluid position as our measurement model since we did not include the position of the contact point as part of state to keep the system group affine. Therefore, we use the relative fluid velocity to form our measurement model. In here, we assume the contact point is stationary, which means the fluid velocity equals to 0 in wood frame. We introduced two different measurement models in the update step. The first one is the 3D position vector of the ground contact point relative to the measurement frame. The second measurement model is the forward kinematics representing the ground contact point position relative to the measurement frame. By comparing these two measurement models, we can find out how much the forward kinematics measurements can affect the filter performance. Note that both measurement models are nonlinear and do not have right invariant observation form, meaning the innovation does not solely depend on the invariant error. Therefore, we need to use standard InEKF procedure here to formulate the innovation and update equations. Here is the overall InEKF design. The state variable of our proposed filter is on the lead group, and the error propagation has log linear equations. But the measurement model does not have the invariant form, so we use the standard extended Kalman filter procedure in here. Here is our experimental setup. As shown in the left figure, the MU sensor, which is along with the 4 markers, is fixed on a rigid plate, and the plate is attached to the subject's pelvis. The position of the markers on this rigid plate is captured by a motion capture system. Reflective markers are attached to the subject lower extremity, which is used to obtain the relative velocity measurement of the ground contact point relative to the measurement frame. As shown in the red figure, 3 different motions have been tested. They are squatting, ladder climbing, and level walking. Also, we perform experiments with 3 subjects. To show the performance comparison between the proposed filter and the state-of-the-art, the contact-based InEKF is also evaluated. This existing InEKF was applied on a Cassie series bipedal robot, where the MU and the measurement frames are perfectly aligned. Here we evaluate its performance when the 2 frames are not aligned. Note that the measurement model of the existing filter has the right invariant observation form. However, our measurement model does not have the invariant observation form. To illustrate the convergence rates of 2 filters, we vary the initial estimated values of the velocity and orientation across 50 trials. The initial velocity and orientation estimates were sampled uniformly from -1 to 1 meter per second and from -20 to 20 degrees. Here is the MU velocity estimation of squatting motion. As you can see, our proposed filter has the faster convergence rates. Once the person doing the squat motion, our proposed filter has a higher accuracy of the velocity estimation. Here is a recap of the velocity estimation of the squatting motion. The gray shaded area indicates the period of standing, and the clear background area is the period of squatting. The improved velocity estimation can be attributed to the higher accuracy of the proposed measurement model under large MU placement offset, which results more effective error correction during the update step of the proposed filter. Here is the estimation of the MU orientation of squatting motion. The yaw angle is not observable under both filters, but both filters have similar accuracy on roll and pitch angle estimation, and we believe that the orientation estimation was relied more on the process model. Here is the velocity estimation of ladder climbing. A noticeable spike can be seen in the y-axis velocity estimation of both filters. This may be because of the inaccurate forward kinematics measurement. Here is the estimation of the MU orientation of ladder climbing motion. Both filters have similar accuracy on roll and pitch angle estimation, and yaw angle is still not observable. Here is the velocity estimation of level walking. Notice that the static contact point assumption may not be valid during walking motion, which can introduce some uncertainties to the filter systems. Yet, our proposed filter has higher accuracy than the existing filter during walking motion. Here is the estimation of the MU orientation of walking motion. Both filters have similar accuracy on roll and pitch angle estimation. We also compare both filters' performance with different measurement models. Here we have the average RMSE values of the 3D vector and full kinematics measurements for the 3 participants and the motions. We found out that the proposed InEKF with 3D vector measurements has the most accurate MU velocity estimation results. This may be because the full kinematics measurement introduced more uncertainties to the filter system than the 3D vector case does. Here is the figure that shows the relative position and the velocity measurements of the right toe in the measurement frame during walking motion. The full kinematics measurement has a noticeable offset on z-axis for position compared to the 3D vector, and the y-axis velocity measurement is also not accurate compared with the 3D vector case. The uncertainty in the full kinematics measurement could be induced by various sources, such as imperfect marker placement, shift of markers on skin or garment. In this work, we propose an InEKF for human pose and velocity estimation with explicit treatment of sensor misalignment. And we did experimental validation with 3 subjects during 3 different motions with 3D vector and 4 KMS measurement models. The experiment shows that the proposed filter has faster convergence and more accurate estimation compared to the state-of-the-art. In our future work, we should improve the accuracy of the full KMS measurement and improve the accuracy of the IMU offset dynamics under more aggressive movements, such as running. We will also test the filter with other types of motions and more human subjects for a longer duration. Here's the reference. Thank you for your attention.